Hey, and welcome to our explainer. Today, we're going to dive deep inside your brain to uncover the incredible, hidden systems that make every single one of your movements possible.
I want you to just think for a second. What's really involved when you do something as simple as reaching out and picking up a pen? It feels automatic, right? Almost thoughtless.
Well, it turns out that simple act is actually a super high-speed, perfectly timed performance. It's an intricate dance managed by two master coordinators working deep inside your brain. So let's meet these two managers. We've got the basal ganglia and the cerebellum. And you can think of their jobs like this. One of them decides what to do, and the other figures out how to do it well. Okay, so let's use an analogy. The basal ganglia, that's your project manager. It looks at all the possible actions you could take and gives the final green light to just one. In this case, pick up the pen. Then you have the cerebellum. It's the quality control inspector, standing by to make sure the execution of that plan is smooth, precise, and perfectly on time. This partnership is the secret sauce behind everything from grabbing a cup of coffee to learning how to play the guitar. So let's zoom in on our project manager, the basal ganglia. I think a better title, though, is the gatekeeper, because its main job is to constantly decide whether to give any potential movement a go or a no-go signal. So technically, it's this collection of neuron clusters buried deep in your brain, and its fundamental job is to pick a winner. When you decide to grab that pen, your basal ganglia has to actively help that specific movement happen, while at the very same time, it has to slam the door on all the other things you could be doing, like tapping your fingers or scratching an itch. And here is the absolutely wild part. The basal ganglia's default setting is to put the brakes on everything. It is constantly shouting, "Stop!" To make a move, it doesn't send a go signal, it just stops sending the stop signal for that one particular action. It's a concept called disinhibition. It literally moves by releasing the brakes. All right, let's trace how this go signal actually happens. It's called the direct pathway. First, your cortex, the thinking part of your brain, sends its intention down to a structure called the striatum. The striatum then does one job: it inhibits the brain's main brake, a part called the GPI. Now, with that main brake turned off, the thalamus is free to shout "go" to the motor cortex, and boom, you move. It's this beautiful chain reaction. You release the brakes by putting the brakes on the brake. Okay, but what about stopping all those competing movements, the ones you don't want to make? That's the no-go pathway. It's a slightly different circuit that ends up activating something called the subthalamic nucleus. You can think of this thing as an emergency brake booster. Its job is to slam on that main brake, the GPI, which in turn shuts down the thalamus, making absolutely sure no unwanted movements get through. Now, this is where our famous friend dopamine comes in, and it is the ultimate efficiency expert. It acts on both pathways at the exact same time. It stimulates the go pathway, that's like pressing the accelerator, and simultaneously, it inhibits the no-go pathway, which is like easing off the brakes. This brilliant dual action system is what makes the winning movement stand out so clearly, allowing us to be fluid and decisive. Okay, so the basal ganglia has given the green light. The project is a go. But who makes sure it actually gets done right? Well, that's where our second manager comes in, the quality control inspector, the cerebellum. The key word for the cerebellum is comparator. See, it's constantly receiving two different streams of information. First, it gets the original plan from the motor cortex. I intend to pick up the pen. Second, it gets real-time sensory feedback from your body. Here's where my hand actually is in space right now. It compares the plan to the reality, and if there's any mismatch at all, it instantly calculates the error and sends out correction signals to get your hand back on track. And that function leads us to a classic clinical question. If the cerebellum is this master corrector, why does damaging it cause something called an intention tremor? That's where your hand starts to shake more and more the closer it gets to a target. Well, the answer beautifully illustrates its job. Without a healthy cerebellum, those error correction signals are slow and clumsy. So as your hand gets near the pen, your brain sees the error and sends a correction, but it's late, so you overcorrect and go past it. Then it sends another late correction, so you undercorrect and go the other way. Your hand just oscillates back and forth, unable to smoothly zero in on its target. So we've seen how this system selects a movement and how it fine-tunes it. But what happens when that very first step, that delicate balance of go and no-go in the basal ganglia, is lost? This, unfortunately, is where we see some pretty well-known movement disorders. The system can really only fail in two main ways, and they are complete opposites. You can either have way too much go and not enough no-go, or you can have way too much no-go and not enough go. And this imbalance leads to two very distinct families of disorders: hyperkinetic, meaning too much movement, and hypokinetic, meaning too little.
And this table just lays it out perfectly. On one side, you have hyperkinetic disorders like Huntington's disease. Here, the no-go pathway fails. There's not enough inhibition, so you get excessive, unwanted, jerky movements. On the other side, you have hypokinetic disorders like Parkinson's disease. Here, the loss of dopamine cripples the go pathway. Now there's too much inhibition, which leads to a profound slowness of movement.
And here is a really, really important point. We're not talking about paralysis here. We're not talking about muscle weakness. The muscles are fine. The direct command pathways are fine. This is a disorder of modulation. It's a failure of quality control. It's like the project manager is just stamping approved or denied on all the wrong projects. Okay, so let's wrap this up. The biggest takeaway here is that every single move you make is a masterpiece of balance. It's not a simple command. First, you've got the basal ganglia acting as that critical gatekeeper, using its clever release the brakes system to pick the right move. Then the cerebellum jumps in to correct and fine-tune that move in real time. And as we've seen, when that initial gatekeeper balance is lost, you either get way too much movement or far too little. And that leaves us with one last kind of mind-bending question. If every single one of our actions is the result of this constant subconscious tug-of-war between go and no-go signals deep within our brains, what does that really tell us about the nature of conscious control? Thanks for tuning in.